Well, I'd like to introduce our first speaker, who is Jesús Santamaría. Jesús is a professor of chemical engineering, and he is vice director of the Nanoscience Institute of Aragon at the University of Zaragoza. He is also the director of the Sanka professorships of nanotechnology, and he is the PI of the Nanostructures, Films, and Particles group at the university. His CV is quite impressive, holding more than 310 publications with an H index of 49. He has 24 patents and over 70 invited lectures. He has also participated in over 80 research projects, including 18 European ones. And I'd like to highlight the fact that he has been awarded twice with the highly competitive ERC Advanced Grant. And his areas of research interest are the synthesis of nanomaterials, nanomedicine, molecular recognition, unconventional catalysis, and nanosafety. And he is going to show us today, I guess, some of the research on nanomedicine that his group is developing.
Thank you very much, Silvia. Thank you everyone for being here. I know it's been a long day. I hope you will find the sessions still interesting, and the coffee also keep you awake for a little longer. Thank you also for the organization to RAID, because this is a good opportunity not only to explain what we do to our Chinese colleagues, but also to know what our colleagues are doing. I had a couple of pleasant surprises this morning seeing what my colleagues are doing here. So it's probably some new collaborations in Zaragoza will also start. Okay, so this is research on nanomedicine, and my group is the Nanostructured, Films, and Particles group. We are at the Nanoscience Institute of Aragon. It's a university institute, and we are also part of the CIBER-BBN. Manolo Blare introduced it this morning. It's a highly selective group. It's only 43 groups in Spain belong to the CIBER-BBN, so it's a network of groups in bioengineering and nanomedicine. Okay, this is my group, some time ago anyway. But anyway, we think that what we are really good at is a synthesis and characterization of nanomaterials, and we take very seriously the highly precise preparation of nanomaterials, because as you know, if you change nanoscale properties, nanoscale characteristics, the nanoscale properties will also change. So you really need highly accurate synthesis procedures, and we are worried about that. So we are, of course, we do conventional wet chemistry, but we are also well-versed in microwave-assisted synthesis. Microfluidics, I think we are the main group in Spain for microfluidic synthesis of nanomaterials. The microreactors allow us to have an unprecedented degree of accuracy in synthesizing nanomaterials. And also, we are one of the few groups, perhaps the only group, that can do laser pyrolysis for the synthesis of nanomaterials on liquid precursors. That gives us also a lot of flexibility. And we put a lot of effort in the scale-up. Sometimes people make nanomaterials, and they can make, maybe 10 milligrams in a week. This is not practical because the companies will come and ask you for tons if the nanomaterial is successful. So we're very interested in synthesis methods. I'm sure you all have heard the expression of nanomaterials in search of an application. Some people create very fancy nanomaterials, very exotic, and there's no application yet for them. This is not in our case. Nothing that we do don't have an application. So the materials that we make, we prepare them, and we apply them in sensors, molecular recognition, mainly explosives and chemical warfare agents. We do microreactors and catalysis, and conventional catalysis, especially plasmon-driven catalysis and microwave-driven catalysis. And today I will be talking about nanomedicine and the things that we do in this area, which is about 50% of the effort in our group. Our group is large for Spanish standard. We are 16 doctors and about 20 PhD students. And finally, nanosafety is also interesting for us. We are very worried about how to handle safely nanomaterials. Okay, so now let's concentrate. In nanomedicine, I will only be able, in the time I have, I will only be able to flash you a few things, and hopefully some of you will be interested, and maybe we can talk later and discuss specific possibilities for collaboration. So synthesis of nanomaterial, what do we do? You name it. I think we are not limited in the type of nanomaterial that we can make. We can make metallic nanoparticles, magnetic nanoparticles, carbon-based, silica, hybrid structures, both dense and hollow, core shell, and of course polymeric. This is especially interesting for nanomedicine. You have here some examples. In the lecture by Dr. Miao, is not here. He talked about near-infrared responsive materials, so you have here several. This is a copper sulfide nanoparticle, hollow gold nanoparticle. This is palladium nanoslabs. Okay, here are polymeric nanoparticles. This is a niosome. These are hybrid structures that contain silicon channels coated with platinum particles and magnetic particles attached on the outside. Really, we can make very sophisticated, highly accurate structures. Okay, a few flashes here. Nanoparticles for drug and gene delivery. This is our bread and butter, okay? This is what we do. We have polymeric nanoparticles, and inside the polymer, which has to be biodegradable and FDA approved, we encapsulate things like triggers for producing the release of the molecule, or we can make pH-sensitive polymers, light-sensitive polymers, heat-sensitive polymers, a variety of functionalities of the nanomaterials, in addition to having the drug inside. This is another example of polymer functionalized gold nanoparticles. Here we are using them as gene delivery agents. So we have the gold particle, we put polyethylene imine and polyethylene glycol functionalities on the outside to make them stealth to the immune system recognition, and also to be able to load a significant amount of genetic material, and that particles are entering very well a number of cells and delivering their genetic cargo there to change the genetic material. Here, this is a very interesting example. We do this in collaboration with the Hospital La Paz in Madrid. This is heat-mediated gene expression. So what our collaborators do there, they make a construct mediated by a heat shock protein, and the heat shock protein controls the expression of a gene. In this case, you can see this is a culture plate, so we put the laser, the nanoparticles together with the cells that express this gene, and we can control the expression of the luminescent gene by controlling the region of laser irradiation. So this is the proof of concept where we go for a mice, for an in vivo model, and we put a gene that controls the vascular expression growth factor. You can see here that this is the control group. This is the mouse harboring our nanoparticles, and you can see that the veins are starting to come out. The vascularization is happening where the laser is touching the skin, thanks to the nanoparticle mediated. And finally, we also have near-infrared activated release from implanted reservoirs. This is a collaboration with MIT, with a group of Bob Langer. And here, this is a rat that has an insulin reservoir that we can activate from the outside using a laser, thanks to a membrane that is a polymer temperature-sensitive membrane that also contains gold nanoparticles as triggers. So remotely from the outside of the body, we are able to use an infrared laser to heat the nanoparticles heat the polymer opens up and releases the insulin. We were able to control the glucose level in a diabetic rat, during 14 days. Okay. Another example of things that we do, this is electrospinning. All of you know what it is, but for those who don't, I remember this is you have a needle with a polymer suspension. It's an electrode needle. You put a 5,000 volts in between the needle and the collector electrode, and this difference of potential stretches the polymer solution, so you can make a nanowire. Nanowire can be anything from 100 to 200 nanometers in diameter, and in that nanowire, we can load anything that is soluble in the polymer, okay? So in that case, for instance, we have put, this is the nanowires, we have put silver nanoparticles, and by a light irradiation procedure that we have controlled, we can control the release of the silver outside and the bacteria killing capacity of these nanowires. Another example, this is nanofibers loaded with hydroxyapatite for bone regeneration, plus growth factor, so this can be loaded with osteoblasts and regenerate bone. And another example of another scaffold with drug-loaded scaffolds for periodontal inflammation. In that case, it contains both antibiotic and anti-inflammation drugs, and this is the release profile. Functional particles, we are very interested in light-mediated therapy. So in the talk by Dr. Mia, you saw some examples of how near-infrared responsive nanoparticles can heat up and kill a tumor if they are inside the tumor. So, but this is one thing you can do. And also you can, in addition to that, you can also use the light to release drug. So you have a synergistic effect in which you are heating the particles, you are killing the tumor by hyperthermia, but also the increase in temperature can be used to trigger the release of the drug that is in the polymer, okay? So for that, also you can, there's one more thing that you can do is also to use upconverting nanoparticles. This means that the particles receive laser of a low frequency, for instance, infrared light, which is the most penetrating one in the body, and emit light of a different wavelength, which is more energetic and create a lot of reactive oxygen species that will kill the cells. So this is a laser, infrared laser. You don't see the light, by the way. What you are seeing here is a shine of the laser through these upconverting nanoparticles, which are semiconductor nanoparticles that are receiving infrared light and emitting in the green, which is, of course, highly energetic. This is carbon nanodots, also a new emerging material, nanomaterial, highly compatible, very easy to synthesize, very cheap compared to these semiconductor materials. It's not toxic at all. And if you dope it with nitrogen, also is able to do upconversion. It's able to take light of a long wavelength and emit light of a short wavelength that will create reactive oxygen species and kill the cells in the nearby. Okay, this is tumor hyperthermia using the Trojan horse strategy that Dr. Martin Duque talked this morning. This is a thing that we do in collaboration with her. So we load our nanoparticles in a mesenchymal stem cell. This is a mesenchymal stem cell. And when you cut it with a focus ion beam, we can do that in our laboratory. We cut it in half, and you see the nanoparticles inside, the gold nanoparticles. And then when you put them in a tumor, they stop tumor growth. Okay, so this is a Trojan horse strategy to deliver nanoparticles to tumors, thanks to the homing ability of mesenchymal stem cells that by themselves go to grow in tumors and sites of inflammation. So we are using a very particular characteristic of the mesenchymal stem cells. And finally, we also have nanoparticles that behave like enzyme. So we call it enzyme-like catalysts. This is a gold nanorod that we have surrounded with a titanium coating, okay? So the idea is that the gold nanorod is able to harvest light of around 800 nanometers, as you see here, and it excites the electrons, is creating what is called a plasmon resonance, which is a collective oscillation of electrons in the gold nanorod. And now these electrons, the hot electrons, are being passed to the titanium coating, okay? And this nanoparticle, this hybrid nanoparticle, the gold nanorod plus the titanium coating, is able to act as a hydrogen peroxidase enzyme without the limitations of pH or temperature that the natural enzymes do have. Okay, in summary, the Nanostructured Film and Particle Group, we are at the Nanoscience Institute of Aragon, and we're happy to collaborate on a variety of issues. First of all, accurate synthesis of nanomaterials in different techniques that are scalable. We are, thanks to being in the Nanoscience Institute, we have access to one of the national facilities, which is the National Advanced Microscopy Facility. We have the best, I think it's fair to say, the best characterization in Europe under one roof in terms of hard materials. So this is a very advanced electron microscopy facility, but also nanofabrication facilities. And because we also are part of the Cyber BBN, we are also part of another national installation, the NanoBioSys, that has state-of-the-art characterization and nanofabrication facilities in terms of biomaterials. Okay, remotely activated drug delivery for cancer treatment, for pain control, for inflammation, tissue regeneration and gene expression mediated by light, light-based therapy, hyperthermia, reactive oxygen species generation, or enzyme mimicking catalysis, and bactericidal materials. Thank you very much for your attention.